Hi, everybody. It's Professor Mitchell. So today we're going to start looking at a couple of sections from Chapter 9, which is on inferences from two samples. We will cover sections 9.2 and 9.3 only. So these are both testing about the difference between two populations. So this section presents methods for using sample data from two independent samples to test hypotheses made about two population means or to construct confidence interval estimates of the difference between two population means. So the difference between these two sections, in 9.2, we're going to work with independent samples. Two samples are independent if the sample values from one population are not related to or somehow naturally paired or matched with the sample values from the other population. In the next section, 9.3, we'll talk about dependent samples. Two samples are dependent or consist of matched pairs if the sample values are somehow matched, where the matching is based on some inherent relationship. So my go-to example is always you're testing to see if a particular diet is effective. So you put 15 people on the diet, you weigh them at the beginning of the diet, you weigh them at the end of the diet. And so in that case, you would want to keep those two samples in the same order. So the first value from the first sample would be matched with the first value from the second sample. Second value from the first sample would be matched with the second value from the second sample, etc. Okay, but that'll be in the next section. All right, so the objectives in this section are to conduct a hypothesis test of a claim about two independent population means, and then to construct a confidence interval estimate of the difference between two independent population means. So the notation we'll be using for population 1, mu sub 1 will be the population mean, x bar sub 1 will be the sample mean, sigma sub 1 will be the population standard deviation, S sub 1 will be the sample standard deviation, and N sub 1 will be the size of the first sample. The corresponding notations, mu sub 2, S sub 2, x bar sub 2, and then I noticed that one of these should be a sigma, and I would have fixed that before we got started, but there was no easy way to do it, so I just figured I'd do it this way. All right, those corresponding notations apply to population 2. All right. The requirements are that the values of sigma sub 1 and sigma sub 2 are unknown, and we do not assume that they are equal. Now, at the end of this section, we'll talk about what you can do if you do assume that these population standard deviations are equal. The two samples are independent. Both samples are simple random samples, and either or both of these conditions are satisfied. The two sample sizes are both large, as in bigger than 30, or both samples come from populations having normal distributions. The test statistic that we'll be using to conduct our hypothesis test looks like this. So it's going to be T equals the difference in the standard, let's try that again. The difference in the sample means minus the difference in the population means divided by the square root of S sub 1 squared over N sub 1 plus S sub 2 squared over N sub 2. Often, mu sub 1 minus mu sub 2 is assumed to be 0. So I'd say in most of our hypothesis tests, the null hypothesis will be that the two populations have the same mean. All right, so since we are working with a student's t-distribution, we're going to need degrees of freedom. So the simplest way to do that is to just use the smaller of n sub 1 minus 1 and n sub 2 minus 1. Note, though, that technologies typically use the more accurate but more difficult estimate given by this formula, which we will never use ourselves. All right, p-values. So remember the p-value approach for hypothesis testing. It's going to work very similar to how we did it in section 8.3, I believe that was. P-values are automatically provided by technology. Technology is not available. Refer to the t-distribution in table A3. And remember that if you're using table A3 to get a p-value, all it gives you is a range. So I tend to prefer technology, but I will leave it up to you to do it whichever way you're comfortable. Critical values we can get from table A3. Don't need technology for that. All right, the confidence interval estimate of the difference in the population means is x bar sub 1 minus x bar sub 2 plus or minus e. So the margin of error e is given by this formula, t sub alpha over 2 times the square root of s sub 1 squared over n sub 1 plus s sub 2 squared over n sub 2. The p-value method, the critical value method, and confidence intervals all use the same distribution and standard error, so they are all equivalent in the sense that they result in the same conclusion. Okay, so here's an example. Listed below are student course evaluation scores for courses taught by female professors and male professors. Use a 0.05 significance level to test the claim that the two samples are from populations with the same mean. Does there appear to be a difference in evaluation scores of courses taught by female professors and male professors? So you can see the sample data here. First, we'll check our requirements. First, the values of the two population standard deviations are not known, and we are not making an assumption that they're equal. And second, the two samples are independent because the female professors and male professors are not matched or paired in any way. Third, the samples are simple random samples, and both samples are small, so we need to determine whether both samples come from populations having normal distributions. And once again, we skip that section on assessing normality. So you've seen before, I've briefly shown you how they do that. They're just asking us to take their word for it that these populations are approximately normal. So all the requirements are satisfied. So the first step is to look at the original claim. The claim is that the two samples are from populations with the same mean. So we're going to express that claim as mu sub 1 equals mu sub 2. Second, we write the opposite of that claim. If that claim is not true, then that means mu sub 1 does not equal mu sub 2. We take those two statements, we decide which one of them is going to be the alternative hypothesis. Remember, that's the one that does not contain equality. So the null hypothesis will be that mu sub 1 equals mu sub 2. The alternative will be that mu sub 1 does not equal mu sub 2. So we proceed with the assumption that mu sub 1 equals mu sub 2, or equivalently that mu sub 1 minus mu sub 2 equals 0. The significance level was given to be 0.05, and because we have two independent samples and we're testing a claim about the two population means, we will use a t-distribution with the test statistic that you saw earlier, which is this one right here. All right, now I'm going to skip one thing which I've shown you a couple times before. They did not give me the summary statistics for these samples. So what you would normally do would be to put these into Excel and then use the formulas in Excel for average to get the sample means and sample standard deviation. Remember stdev.s. and that's how you would calculate those. All right, so the test statistic is calculated using these statistics. For females, N equals 12, X bar equals 3.866667, and the sample standard deviation is 0.563. For males, N equals 15, X bar equals 3.993333 equals 0.9545. So you plug all those numbers into the formula. This is definitely something that you should try right now. Hopefully you have your calculator handy. If not, pause the video and grab your calculator, because you can see this is a pretty complicated formula. So I just want to make sure that you are putting it into the calculator correctly. All right, so it doesn't matter which sample you call number 1 and which one you call number 2, as long as you are consistent, all right? So they're using number 1 for females and number 2 for males. And let's see, so X bar sub 1 minus X bar sub 2 looks like this. Remember, we're assuming that mu sub 1 equals mu sub 2. That means that the assumed difference in these population means is 0. And then you plug in S sub 1, N sub 1, S sub 2, N sub 2. You get this. And the calculated test statistic comes out to negative 0.660. I will point out that if you made males number 1 and you made females number 2, this would come out to positive 0.660. Since we are doing a two-tailed test, it doesn't matter. Okay, so the p-value with test statistic t equals negative 0.660, we refer to table A3, which I will show you in a second. The number of degrees of freedom is the smaller of N sub 1 minus 1 and N sub 2 minus 1. So remember, there were 12 females and 15 males. So we're going to use the smaller of 11 and 14 for the degrees of freedom. So that would be 11. With 11 degrees of freedom and a two-tailed test, the reason it's two-tailed is because our alternative hypothesis does not equal. Table A3 indicates that the p-value is greater than 0.2. So let's have a look at that. So I am going to pull up table A3, which is right here. So remember, the way this works is you go down to the degrees of freedom and you look for the closest t-value to the calculated one. And remember that if it has a negative sign, you just ignore the negative sign. All right, so we go over to here and we find that the closest t-value to our calculated 0.660 is 1.363. And I think I'm actually going to bring up my tablet for a second, because I think I just realized there might be a mistake in the PowerPoint. So bringing up my tablet. Okay, I changed my mind. I actually don't think they made a mistake, all right? But I think it might be a good idea to show you this picture anyway. Let me just make sure. Yes, we're good. Okay. All right, so what we have looks like this. So here is my t distribution. This 1.363 that we just found. So what I didn't notice when I thought that they had made a mistake was that remember, at the top of table A3, there's one row that says one tail and there's one that says two tail. So at 11 degrees of freedom, the 1.363 actually cuts off 0.10 of the distribution. Okay, but then there's another row that says that that t-value corresponds to an area 0.20 in two tails. And this is a two-tailed test, so that is the one that I want. Okay? So this area is also 0.10. Our calculated test statistic, might as well use the negative one, is negative 0.660. So our p-value would be the total combined area between here and, not between, but out here and out here. So by comparing our calculated t-value to the one that's in the table, we can see that this combined area out here and also here, that combined area is greater than 0.2. Greater than 0.2. So what we're going to do here in a second is bring up my favorite website, StatTrack, which will give us a more precise value for the p-value. All right, so let's have a look at that. Go back to the screen. I'm going to bring up my browser, and I have already typed t-distribution calculator into Google. I'll just make this a little bigger. There we go. Okay. So that brings up StatTrack. I'm going to click on that. Okay. So random variable is the t-score. The degrees of freedom is 11. Now, I have to be careful what I type in this t-score box. So our calculated test statistic was negative 0.660. I'm going to go ahead and put that in. Okay, but I want to point out before I hit calculate that the value that's going to come up in the box below that is going to be only the area to the left of 0.660. So if you picture my drawing a minute ago, it would be only the red shaded area on the left. Okay? So what I'm going to do to get my p-value is I'm going to double whatever the value is that comes up here. So I hit calculate. I get 0.2614. All right. So that's actually going to give me a p-value of 2 times 0.2614, which is 0.5228. Now that's a little different from the one that they got using technology, and that's because I think that they sort of let their technology do the whole thing. And so they use that fancier formula for the degrees of freedom. Okay, so let's go back to the presentation. Get rid of this. Okay. All right, so yeah, we got 0.5228, they got 0.5172. Okay, in any case, because the p-value is greater than the significance level 0.05, we fail to reject the null hypothesis. So I never get tired of telling you the interpretation of that p-value. In a world where the two population means are equal, the probability of finding a sample of men and a sample of women who differ by the amount that our sample differed by at least that much, that probability is like 0.5228. It's actually more likely than not that it would differ by that much. Okay? So that is hardly compelling evidence to reject the null hypothesis. So we're going to fail to reject the null hypothesis. Remember, when you have a high p-value, if p is high, the null will fly. If p is low, the null must go. Okay? So the interpretation is there is not, and remember to word this in terms of the original claim. The original claim was that the two population means are equal. We have not found good evidence to the contrary. So we're going to say there is not sufficient evidence to warrant rejection of the claim that female professors and male professors have the same mean course evaluation score. We have not found evidence to contradict that claim. Okay, so again, the tricky part about the p-value approach using the table is that it only gives you a range for the p-value, and determining that range is often somewhat difficult. Technology automatically provides the p-value. So you see they used XLStat and got a p-value 0.5172. They just fed all of the summary statistics right into XLStat, and they got this slightly different p-value from the one that we got. But it would lead you to the same conclusion. Okay, the critical value method of testing a claim about two means is generally easier than the p-value method. For one thing, there's no need for technology. You can do everything with the table. With N1 equals 12 and N2 equals 15, the number of degrees of freedom is 11. In table A3, with 11 degrees of freedom and alpha equals 0.05 in two tails, we get critical values of t equals plus or minus 2.201. Let's have a look at the table to see if we can see where they got that. Okay. So we want the area in both tails to be 0.05, so we're going to use the middle column. And if we go down to 11 degrees of freedom, there's 2.201. Okay. So our critical values are plus or minus 2.201. Remember, with the two-tail test, you have two critical values. Okay, and they drew a nice picture of what these critical values represent. They're using the ones they got from technology, which are a little different. Okay, so this green shaded area out here is called your critical region. Our calculated test statistic was negative 0.660, which is clearly not in the critical region, which means we are going to fail to reject the null hypothesis. You would reject the null hypothesis if your calculated test statistic landed in the green shaded region. Okay, so now an example of a confidence interval. Using the previous data, we're going to construct a 95% confidence interval estimate of the difference between the mean course evaluation score for female professors and for male professors. So before we get into this, I just want to say again that it really doesn't matter which sample is number one and which sample is number two. When you're doing your homework, the homework might specify which one they want you to make number one and which one they want you to make number two, and then that way the computer will have an easier time recognizing if your answer is the same, answer that's been programmed to be correct. But ordinarily it doesn't matter. It looks to me like they're going to use females for number one again, and males, females and males. I would take that to mean female minus male, but it really doesn't matter. Okay, because we're using the same data from the previous example, the same requirement check applies, so we don't have to check those requirements again. First, find the value of the margin of error, and that's with this formula right here. So in table A3 with 11 degrees of freedom and alpha equals 0.05 and 2 tails, we get the same critical values that we got just a moment ago. Oh, and this time they're using the ones from the table. That's nice. Okay. So T sub alpha over 2 is 2.201. And using those same summary statistics that we used before, you get that the margin of error is 0.422452. All right, remember that the two sample means were 3.86666 and 3.993333. So the confidence interval would be found like this. You do the difference between the sample means, which is going to be about negative 0.12 something something, and plus or minus the margin of error, which we just found was about 0.42. And we get that the confidence interval estimate for the difference in the population means is between negative 0.55 and positive 0.30. Note that you would get slightly different results using technology, but it's pretty close. The important thing about this confidence interval estimate is what they say here. We are 95% confident that the limits of, now they're using the technology ones, negative 0.53 and 0.27, actually do contain the difference between the two population means. Because those limits contain 0, this confidence interval suggests that there is not a significant difference between the mean course evaluation score for female professors and for male professors. Okay. So if you were using this approach to do your hypothesis, this would not be strong evidence against the claim that the two population means are equal. All right, really briefly, and you're going to see a little bit of this in lab number 12, if you're taking Math 1600. Assuming that the two population standard deviations are equal, you can pool the sample variances and get slightly more accurate results. The pooled estimate of sigma squared is denoted by S sub p squared, p for pooled, and is a weighted average of S sub 1 squared and S sub 2 squared, which is used in the test statistic for this case. So notice it is a similar formula as the one we were using before, except we're just using S sub p instead of S sub 1 and S sub 2. And here's how you calculate the pooled estimate for the variance. S sub p squared is equal to n1 minus 1 times S sub 1 squared plus n2 minus 1 times S sub 2 squared divided by n sub 1 minus 1 plus n sub 2 minus 1. And in this case, the degrees of freedom is n1 plus n2 minus 2. So it gives you, it allows you to use a higher value for the degrees of freedom than if you kept the samples separate. All right, so we're not going to do an official example. Again, if you're taking Math 1600, you will see one in lab number 12. There's also one in the homework, and of course, I'm happy to help you with that if you need it. This is how you would find your confidence interval. So it's exactly the same formula. You just calculate E. And here's how you calculate E. E equals T sub alpha over 2 times the square root of S sub p squared over n1 plus S sub p squared over n2. Here's that formula for S sub p squared again, with degrees of freedom equal to n1 plus n2 minus 2. In reality, the population standard deviations at sigma 1 and sigma 2, didn't notice that before, let's fix that real quick, are almost never known. But if they are somehow known, the test statistic and confidence interval are based on the normal distribution instead of the t distribution. Okay. Other than that, it's a very similar formula to what we were using. This is how you find your confidence interval. This is how you find your margin of error in that case where sigma 1 and sigma 2 are known. The recommended strategy, though, is to assume that sigma 1 and sigma 2, ever type this, I'm just going to put S's here to start with, and they'll go back and change them to sigmas, and then they forgot to do that. Assume that sigma 1 and sigma 2 are unknown. Do not assume that they're equal. These are sigmas again, because remember, we can always calculate S sub 1 and S sub 2. And use the test statistic and confidence interval given in part 1. You only use these alternative methods if you know, first of all, that the two population standard deviations are equal, or if you actually know exactly what they are. But normally you don't know that. And that's going to do it for section 9.2.